Hi to everybody. I'm Stefano from Turin, Italy. And I'm starting from a question for you. How many people are here in the room are handling every day with healthcare data? Okay. I pray also for you because handling healthcare data nowadays is a mess. It's a completely mess. So let me explain some issue we have with health data. The main is the lack of any standardization. So without any standardization, it's quite impossible to compare direct data between different formats and then combine data from different sources in a way that there is something good as a result. Because if we have different sources that making different data formats that are incompatible with each other, it's very difficult to have a very path to the final result for a statistical point of view. Then there is privacy and security concern. We are handling with health data, so health data is very sensitive and it's the most confidential data we have about people. And so there is also security problem. So normally when we are managing with the health data, the first step is just to anonymize all the possible data inside to avoid any match between the data and the patient related to that data. This is the first step, and this is mandatory because when we go on with the statistics, we cannot have any information deeper on a precise patient because this is in European illegal because we have a lot of concern when we get this data from different sources from the same patients. Then there is another point. This is also critical. There is a lack of quality of the data. This is the main reason is the device that acquiring the data. That some way there are manufacturers and not all are very well certified. So we have a data that maybe sometimes should be inconsistent. And also when we have a certified device that is okay for the certified body, then we have also the patient that maybe he have not the training to make the recording correctly. And so the measurement or the data we provide from the patient is not in the correct image of the patient itself. So we have all these issues. All these issues then have the effect that we have, when we try to combine them, we have the problem that the statistical analysis we have at the end, if the input is useless or there is some strange things inside that we cannot discover because we have not the way to discover how the data is correct or not, then maybe sometimes the statistic we get is completely useless without any use. It's not useful, and at most it's not accurate. The accuracy is very few or less. to avoid this problem, there is a development of data standards and protocols in progress. And also the GDPR tried to also cover health data, not all aspects, but some of them. And the process we need to have with health data also have a need of investment for data infrastructure analysis tools, because we are growing and growing data about people. And we have a lot of problems. For example, for the first step, the anonymization step is a step that it can make a lot of time, computational time. So the investment in the data infrastructure is very important. So we return to the first point, so the lack of standardization. We have a vast and complex universe of data formats inside the healthcare. So one of the challenges is in this universe that, like the real universe, it can explode. And the problem is the new formats entering the universe are mostly proprietary. And this is a big problem when we are trying to handle with the data. So it's, there must be a way to try to define a guideline to create new formats. And the best way we suggest is to try to use open format. Why open format? Because normally when a manufacturer of medical device creates a new device, it doesn't know, like we told before, there is not a standardization. So when it starts, it just creates, okay, I have this data, okay, I put in a format that I invented, I created for my device specific. But the problem, we have a lot of devices and a lot of data in different formats. So in the past, the best was, okay, we have different formats. We can create a converter to an open one and then make the comparison, the combining with an open format. But this converter normally is made by the same manufacturer of the device. So a lot of time, this converter is also proprietary. And so we have now access to the source code. So if there is some error in implementation inside the converter, we don't know. So we just convert to the open format, but we don't know by sure that what we get is exactly the same we have in the as input as original format, original proprietary format. So this mismatch is also a real problem. We cannot solve that. So, as I told before, the importance of using open format, it gets the best for avoid all this problem. But when you create an open format, then you have to adhere to this open format. You have not to create a proper extension to our open format, because if you want to create an extension, you have to discuss to the open community and then try to change the open format, not trying to put something proprietary in an open format without any description of this extension, because at the end you get the same proprietary format at the beginning. And so the use of the open format also allow the collaboration, allow also the research in healthcare. So this is a list of some open formats that are in healthcare. There are some, not all. The main one is EDF, that is European Data Format. and BDF, biosemi data format that used for medical time series. What does mean? ECG, EEG, whatever in the timeline we have a measurement, we can transform this data in this type of format. This is our open format. They are an open page with research mainly from the university that maintain the format, increase the version for each major version, and describe very well the format. Then we have the ISHNE. The ISHNE is the International Society for Alter and Non-Invasive Echocardiography. Is a format that is dedicated for the Alter, EKG Alter. So it's another way, like EDF. EDF is more open to other data inside, so we can use the same to other medical time series different from Alter. ISHNE is dedicated to Alter, so it's created for this society just to, it's an old format. EDF is more recent, like format than ISHNE, but it's very simple to use. Then we have the open format for biological sequences, so DNA and protein, whatever. So this is FastI, FastQ, and SAM. This format has just the way you put the single character in a line to describe the sequence. But the sequence in each format is described in different way. And so there are different open formats for these biological sequences because there are different interpretations of the data inside. Then we have the digital imaging for communication in medicine that is used for medical images. So CT, RMI, and other images like that. And the ICOM different between other formats described in this page are also the description of the protocol. The interconnection is also described in this format. So it's not only the description of the images, but also how that should be transmitted each from one part to another one. So go to Python, because we are in EuroPython, so we have to talk about Python. Python is used for analytics. So with Python, we can manipulate, analyze, and have a complete data set, and we can make comparison between data inside the Python. So what we can compare, the main one is patient information. Okay, you told before that you have no patient information because we have anonymized. No, we normally when you anonymize healthcare data, you maintain the age and the sex, or something like that. Some information you have to maintain to make statistical data. So normally this information is used for statistical data, and so we can manipulate, analyze, and compare. And so also when there is some pathologies, is normally inserted in patient information. Then there is the result of blood analysis that is another test useful to detect some pathology and to make statistics. Then ECG, EGG, echography, radiography that are images. So I suppose that you know the one in the left part of this slide. There are a normal library to handle with statistical data. So we have NumPy, SciPy, Pandas, and Matplotlib. They are standard ones. Then in healthcare data, we also have another ones that combining with them, they make it possible to reading, manipulate, and using the Matplotlib, for example, to visualize the result. So we have BioPython, MNE-Python, PyDicom, ADF-lib-Python, and Ishner-Alter-lib-Python. From the name, you can discover that the large tree libraries are dependent in each format they support. So PyDicom is for DICOM, ADF-lib-Python is for ADF, and Ishner-Alter-lib is for Ishner. BioPython and Python are more complex. They have a lot of formats inside and are more specific. So we go inside. BioPython is for biology and bioinformatics. So the formats we told before about biological sequences are manipulated, are accepted by the library called BioPython. So with this library, we can make, describe, and also create protein structure, making population genetics, handle biological sequences, and making annotation on them. So we have the input and output from this open format we told before. BioPython also supports proprietary formats, some proprietary formats, not all, and allow the possibility to export in open format. So it works like a converter. So this one is an open converter for healthcare data in biology and bioinformatics. Also, I have inside some machine learning. There is some classes inside BioPython that allow to have manipulation using machine learning. So this is an example with BioPython, including sec.io. You can parse a general bank file with inside a protein or whatever you want, and then you can cycle in the genome inside the file and create a single phase file as output. So this is a conversion written in 4 lines. Normally, to make this with another software or with a proprietary software, it's like a mess. BioPython is very simple to use and allowed to handle with a lot of proprietary format or different format without any problem. Then we have MNE-Python that is concentrated to magnetoencephalography, electroencephalography, stereo encephalography, electrocardiography, near-infrared spectroscopy, and other ones. And allows also difference between BioPython. It allows also the visualization and exploration of the file. So using matplotlib and other libraries to visualize the result, it's allowed to handle and visualize immediately the result of what you want to get. It supports more format than BioPython, and he has inside a lot of converter format from proprietary format to open formats. The problem is that he has also permissive reader. Permissive reader should be a problem in healthcare data because we go on in this point after, but if we have a library that have a permissive reader inside, then if the original data has some deviation from the open format, then the permissive reader doesn't detect that and allow, for example, a proprietary extension to the open format. So, for example, if we pass a not valid ADF file to MNE, we can plot. So, yes, we can read this file, but we have not the detection that maybe this file is not correctly in adherence with the open format. So there is no warning, no error, no issue at all. For me, it works like that. I can read, and I have no idea if there is some error inside the data format. I don't care. I just want to get the data from. This should be a problem, because if we don't guarantee the open format, then whatever can make extension to the format. And the problem is that the manufacturers have to comply to open format, because without this, we cannot have an open format right. So we have to have the strict reading of the open format. For example, the library we told before, the EuroPython, Python, if the file is not complete, it just not open. It just say, okay, this is not valid. And it check whatever in the open format is written, so it check all the definition, and if it's all correct, then it's go on and open the file. This is the right way to do. Because other way, we have the possibility to include some proprietary format and also support that. That is not the best, because to have the possibility to compare, we have to avoid the support of proprietary extensions. Then we have PyDicom for medical image dataset. It also supports the protocol, so we have storage transfer, and quindi the protocol implementation. With PyDicom, we can plot directly the image inside the DICOM. So if I pass the file from DICOM, my leg, I can plot directly from inside the PyDicom with a few lines. This is very simple to use, and also there are DICOM server and client that are written using this library, because it implements very well the protocol. So let's make an open format. We can try to make an open format from healthcare data, just very simple, to try to get something that anybody else can use. So for example, we can use the blood pressure, the device that measures the blood pressure. So we can create just a simple JSON file that is open, and then try to make a constraint to avoid that people can not create a proprietary extension and not exchange without the community approval. Why we start with the blood pressure? Because with blood pressure there is no right standard, so we can make one in a very simple way. So we just create an array with daytime and all measurement we can take from the blood pressure. So the daytime, and then the mode automatic or manual, dependent of if the device is automatically measurement, or if it's manually measured when someone presses the button. So we can add also other information, like the patient information and the intervals. For the automatical blood pressure, ambulatory blood pressure, there is the possibility for the device to make automatic measurements during the day and during the night. And normally these are dependent on time. So normally there is morning time and night time. From this point, it starts with a different interval. So we just make this interval as an argument, as a possible field inside the JSON file. So this also can be customizable, because should be a setup for the device. And so also we can add error, because there are also errors when the device can make the measurement. So the formats have to also support error. There are some formats that doesn't support error because they only want to get patient data. But the problem, if we cannot get the error from the device, we cannot know if the device is working correctly. So, okay, I get the patient data, but the device doesn't work very well because it makes a lot of error. I don't know that. So the format has also to store if the device makes some error. And then we create a version of the format. So the format has to be versionable. And also we can add some information from the device, for example, the firmware of the device, something like that, just to add more information to the format, because the more information we have inside the format, more accuracy we have. And then, okay, we have the JSON file with all the data we show before, we get before, all one after other. And so we have a big JSON file with all measurement, with the device information, with the patient information, with error information. So we can create a schema to validate the JSON. So there is a JSON schema format that allows the possibility to create a definition of the JSON, so we can validate. But we work with Python, so we just make a Python do that. So there is a library that is called JSL that allows to create the JSON schema for you. So you just describe how do you want the schema and also the JSON like, and you can get the schema and then validate the JSON you create is valid. Why I create a JSON file? Because normally, as I told before, the blood pressure create a proprietary format that sometimes you get the information how the manufacturer create this binary, and you can convert. So you need to convert to make conversion more easily, because having this format sometimes is not the best to make conversion and then statistical analysis. So after making a schema and example of about this format, then you have to create a library to support the format. When you read the format, you have to check the adherence to the schema. And then, like I told you before, you have to create a converter from another format to your format. And then the last point, but the main one, you have to spread the open format. That's all. Any question?
Hi, nice talk. Do you know if these libraries can connect with FHIR files?
Yes, SS7 and FHIR, sorry, can using this library without any problem. It's FHIR are a protocol, so it's like a container. And inside this container, you can use different formats. So you can use whatever of this library you want.
Hi. Quick question. You were talking about healthcare formats, especially open source one. I was wondering if you had a look at the LC7 or IHE kind of formats that are also open source and kind of widespread in the industry, especially for raw measurement and mission data and that kind of stuff.
Yeah, SS7 and FHGR are mainly for communication, and also are container for other formats. So you can use to put proprietary format inside this container and then put it to another one. So it's not the main of the purpose of the talk. But yes, are open also this, but are communication protocol more than data formats. Any other question? Thank you.